We've been talking about the connections between magnetism and electricity. For instance, if there's current flowing through a coil of wire, that coil has a magnetic field and acts like a magnet. Another connection is that magnetism can cause currents. And I'm going to give it a definition here. An induced current is a current caused by a magnetic field. And one way that is maybe easy to visualize, maybe not that useful, is this one. If I take a wire and I move it through a magnetic field, for instance, this wire is moving to the right in this magnetic field, it's going to cause a current. Here's why. If I think of each charge in this wire, each plus Q charge, it's moving to the right. So charge of plus Q is moving to the right. Now, our first connection between magnetism and electricity is if there's a charge moving in a magnetic field, it's going to experience a force. And we use the equation F equals Q VB to find the force on it. We also used right-hand rule number 1 to find the direction of the force. So we'll do that for this charge. This charge is moving to the right, and when we do our first right-hand rule, our thumb goes the way the charge is moving. So we have to point our thumb to the right. Our fingers do what the magnetic field is doing, and the X's stand for into the page, so our palm pushes into the page. Our fingers push into the page. So our palm then is pushing towards the top of the page. So there's going to be a force upward on the charges in the wire. So by the first right-hand rule, there is going to be a force upward on that plus Q charge. So it's going to start moving up through the wire, and that's going to give us a current, because current is defined as the motion of charge. The equation we're going to use for this is curly E, and I'll describe what that curly E stands for in a minute, equals B L V sine theta. B is a magnetic field, V is the velocity, L is the length of the wire, and theta is the angle between the motion of the charge, or the motion of the wire, and the magnetic field, like it was in QVB sine theta. Again, it's almost always going to be right angles, like it is for this. They're moving to the right, and the magnetic field is into the page. Those are at right angles to one another. This curly E stands for electromotive force. Sometimes you'll see that abbreviated as EMF. And it sounds kind of scary, but it's actually very easy if you know that it is equivalent to voltage. Okay? In our electricity unit, we call voltage potential, or potential difference. In this case, we're going to call voltage electromagnetic force. So here's an example using that equation and this idea of moving a wire through a magnetic field and getting a current. So in this case, the loop below has a resistance of 2 ohms sitting in a magnetic field of 4 Tesla. So we have R here is 2 milliohms, sits in a magnetic field, that's B of 4 Tesla. The length of the wire, so that was L, is 0.3 meters. I want to know the velocity, and I want the current to be 0.5 amps. So whenever I see a wire sliding across a magnetic field, I'm going to use this equation, the EMF equals BLV sine theta. The problem is I don't have the EMF for this particular problem. Okay, but if you remember, EMF is equal to V, so I can use this fact, E equals V, and V equals IR. We use that equation a lot in our current electricity unit. So I'm going to replace this curly E with IR. Then IR equals BLV sine theta. Again, we're going to ignore the sine theta because they're at right angles. So now I can start plugging in. I get 0.5 times my R of 2. Now it's millitesla, so I got to remember milli is 10 to the minus third, equals B, which was 4. L was 0.3, and I'm looking for the velocity. So this gives me 1 times 10 to the minus third equals 1.2 V. If I divide by 1.2, I get V equals 8.3 repeating times 10 to the minus fourth meters per second. Now we also want to talk about the direction of the current. So using our right-hand rule, we'll imagine a positive Q here. My thumb points in the motion of the charge, so as the wire sweeps to the right, the charge will move to the right. My fingers point into the page, which gives me a force upward on the charge. So it's going to start moving up this way. Now, that's going to force the current to flow to the left in the top wire and around like this. So the direction of our current is counterclockwise around the loop.